Hello, everyone. Do you have my voice?
Yeah.
Yeah, we can hear you.
Okay, thank you very much. So this is our first meeting. This is linear algebra, math 310. Let me just remind you of a few things, and then we would start with linear algebra. So there are a few dates that I want to remind you about them. They're quite important. So Professor Vero, Professor Vero, as you probably know, he's going to lecture on February 4th and 9th. Lina she's going to lecture on February 11th and 16th. Your first homework, the due date for your first homework is February 17th. And also we would have our first midterm on February 18th. Right? And as you know, after that, some of you will move to math 315, and some of you will stay at math 310. Okay? So just have these dates in mind. Okay. So let's start to speak about linear algebra. So I think you didn't have any lecture before this because the class yesterday was canceled. So I think this is the first meeting. I'm just going to review some very basic things, especially because, like last one day. So I'm gonna start with some basics. So linear algebra.
Sorry, could I ask a question before you start?
Yes, sure. Yeah.
For the math 315 is taught by Vero, and math 310 is taught by Alina, right?
That is correct.
Okay. Thanks.
Yes. Also, yeah, that was also. Thank you. It just reminded me of this thing. So this class is supposed to be very interactive. So I really like you to turn on your webcam, turn on your camera, if your phone or if your computer has a webcam or camera, so we can unmute yourself so we can discuss things. I'm not going to lecture here. Here we can just talk about like problems, questions you have, and yeah. So that would be great if you turn on your webcam. Okay. So linear algebra, the object of studying linear algebra are these things. So the object of the study is, it's about vector spaces and linear equations on vector spaces. So let's start with vector spaces. So the first step is to just define and understand what vector spaces are. In order to define vector spaces, first we should go one step backward and talk about fields. Okay. So let's start with one example. You are probably all familiar, you're familiar with real numbers, right? Real numbers. So all positive and negative numbers, it contains all rational numbers, also irrational numbers. There are some very, very basic properties that the real numbers, they satisfy, right? So for any two real numbers, say A and B, for any two real numbers, we have addition, we have A plus B, and we have multiplication, A times B, okay? And there are some very basic properties these two operations have. So I would just list them. One of them is associativity. Okay, that means if I take three real numbers, A, B, and C, If I first look at b plus c, if I add these two numbers, and then I add a to them, so a plus b plus c, but it means first we add b and c, and then we add a. It would be equal to a plus b plus c, right? Simple. Okay. And second, the same thing is correct for multiplication. If I multiply b by c and then multiply that by a, it would be equal to a times b and then multiplying that by c. Okay. The interesting thing is that although these two properties are very trivial for real numbers, they are not correct for any system of numbers. And in mathematics, at some point, you might work with other system of numbers that they really don't satisfy these simple properties. So that's the first property. The second one is commutativity. So a plus b is equal to b plus a, and a times b is equal to b times a, right? Fairly simple. That's a simple property of real numbers. The third one is there are additive and multiplicative identity. So there is something called additive identity. What do I mean by that? There exists a number which if you add that number to any other number, it doesn't change that number. And that number is actually 0. So any number plus 0 is equal to 0 plus that number is equal to that number itself. It doesn't change anything. And the same is correct for multiplication. So we have multiplicative identity, which that is 1. Any number times 1 is equal to 1 times that number equals to that number itself. Multiplication by 1 does not change anything. Again, although these properties are trivial for real numbers, there are other system of numbers that they do not have identity elements. Okay, the other interesting property is having additive inverse. For any number a, there exists another number such that if we add these two numbers, we would get 0. The 0, remember, is additive identity. And that other number is simply minus a, right? And the same holds for multiplicative inverse. Any number, for any number which is not 0, for any non-zero number, there exists another number which if we multiply them, we would get multiplicative identity, which is 1. That other number is 1 over a. Okay, good. And the last property is the fact that multiplication distributes over addition. If we look at b plus c, and then if we multiply that with a, we would get a times b plus a times c. So real numbers, they have all these properties, right? Any other system of numbers, any other set of numbers which they satisfy all these properties, they form a field. There are other examples. For example, the set of real numbers is one example. The set of complex number is another example. The set of rational numbers is another example, and there are many more. Okay. And it's fairly simple, right, to check these properties for these set of numbers. So let me ask you a few simple questions. Let's consider n. Is n a field or not? With the ordinary addition and multiplication we have on n. Is that a field? You can unmute yourself and answer.
Yes.
Okay.
No, because there's no multiplicative inverse.
Okay. Okay, we have both yes and no. Thank you. Okay, so let's see. I should check all the properties. The first property was, okay, let's get something straight first. This is more about convention. What is n? Is n the set of numbers 1, 2, 3, etc.? Or do you define n to be the set of 0, 1, 2, 3, etc.? Which one is your definition? Let me look at Wikipedia to see which one is the more. Let's see if there's any comment about that. Would you take 0 as an element in the set of natural numbers n, or you don't?
I just do what's convenient.
Okay. Okay, let's take the second definition. Let's, for the moment, say 0 is a natural number. Okay. Okay, so we should see if we have addition and multiplication. Of course we have. Any two natural numbers, we can consider their addition. It's again a natural number. That's what matters. And for any two natural numbers, we can look at their multiplication. Again, it's a natural number, so that's good. So we have addition and we have multiplication. That's usually the notation. So this set of natural number comes with two operations, addition and multiplication. Okay, so the first property was associativity. For any three natural numbers, we should check if a plus b and then plus c is equal to a plus b plus c, which means first we look at b plus c and then we would add a. Is it correct? Yeah, of course. I mean, doesn't matter if we have like 3 apples and then we add 2 more apples and then we add 5 more apples. It doesn't matter in which order we're counting them, right? That's correct. Same holds for multiplication. That's also correct. Okay, commutativity. That's correct. For any two natural numbers a and b, a plus b is equal to b plus a, and a times b is equal to b times a. That's good. Let's get to having the identity element. So is there a natural number such that if I add that number to any other number, I would get that number itself? Yes, with our definition, yes. We assumed 0 is a natural number. So we have the identity element for addition. What about multiplication? Do we have a natural number that if we multiply any element by that, we would get that number itself? Yes. Again, 1 is a natural number. So because 0 we assumed in our definition is a natural number, and also 1, these two are correct. Let's get to the inverses. For any number a, is there another natural number such that if I add them, I would get 0? Is that correct? The answer is no, right? Because, for example, let's say take 5. What is the number which I should add to 5 to get 0? It's -5, right? -5. But -5 is not a natural number. It's negative. Remember, with our definition, natural numbers is the set of non-negative numbers, positive and 0. -5 is not in n. So if you're looking for a natural number, which if I add that number to 5, I would get 0, I can't find anything. So that axiom, that property of fields does not hold here. Furthermore, we don't have multiplicative inverse. Is there a number? Is there a natural number, which if I multiply that by 5, I would get 1? Again, no. That number should be 1 over 5, but 1 over 5 is not a natural number. So if I'm working in the set of natural numbers, I wouldn't find anything to put here, right? And that's exactly the problem. The set of natural numbers, therefore the set of natural number is not a field. Okay. Similar things, almost similar arguments hold for the set of integers that is not a field either. Well, over Z we have additive inverse, right? For any number, for any integer, say 5, 3, -3, there is another integer which if we add them we would get 0, but there is no multiplicative inverse again. So again 5 is in Z, but there is nothing in the set of integers, which if I multiply 5 by that I would get 1. But 1/5 is not in Z. And therefore, Z is not a field either. So one thing you can check, I wouldn't do it here, is that the set of rational numbers is a field. So if you look at all the numbers, which they can be written as P over Q, where P and Q are integers and Q is non-zero, the set of fractions, the set of rational numbers, that is a field. Okay. So that's the first step. I'm sure Algebra will talk a lot more about fields. I'm sure he would go to more abstract mathematical theorems, and we can talk about them after Professor Vero talks about them. Okay, so that's what we mean by a field. Usually in this course, we take our field to be either real numbers, the set of real numbers, or the set of complex numbers. Okay, it's one of them. Is there any question up to this point? No? Okay. Okay, the second concept which we are going to deal with, and it is important, is the concept of vector space. So vector space is what you probably already have in mind. It's something like, for example, R2 or R3, or more generally, Rn. Like vectors, right? Like vectors in plane, vectors in three-dimensional space, and etc. So again, we can, if you consider, for example, R2, R3, vectors in R2 or R3, they have some basic properties, okay? So I would show any vector space usually with this notation with V. So V can be something like R2, R3, or other things, which we will see later, more complicated vector spaces. And any vector inside that space, I usually show that with a notation like this, with one arrow above it, okay? Now, vector spaces are defined over a field. So for example, R2 or R3, they are defined over the set of real numbers. We say these are vector spaces, which they are defined over the set of real numbers. What does that mean? It means any vector I take inside these vector spaces, for example, if I take a vector inside R2, this vector is gonna be something like this. I don't know, say 2 and -1, right? I would say this vector space is a vector space over the set of real numbers if I can multiply u by a real number. So if I take a real number, say 3, I can multiply this vector by 3. And that simply is 3 times 2 and 3 times -1, which is 6 and -3. Okay, so let me write down the definition of a vector space in a more axiomatic way. So we would say V is a vector space over a field. Let's show our field with f. Here, you can assume in your mind, you can just suppose f is just r or c. It really doesn't matter at this point. I would say V is a vector field, vector space over a field f if it satisfies the following properties. The first one, again, is associativity. Again, by that I mean if you take three vectors, u, v, and w in V, three vectors, you know we can add vectors together. We can look at v plus w. We have that. We have this operation over vectors. For example, if you think about vectors in R2, it just means we are adding components, right? And then we can add u. And this operation should have this property that u plus v plus w is equal to u plus v if we add them first and then add w later. It's very similar to the associativity which we had for fields. The second one, again, is commutativity. Again, here, I want u plus v, the sum of these two vectors, to be equal to v plus u. For vector spaces in general, we don't have, for vectors in general, we don't have a notion of multiplication, right? For example, if you take a vector u equal to, I don't know, 2, 1, and take another vector v minus 1, 3, there is no natural notion of multiplication. Unlike elements of fields, we can't say what is really the multiplication of these two vectors. Remember, if I'm supposed to have a multiplication, the multiplication of two vectors should be another vector. And that's not something that we would have on any vector field. For example, on R3, we have some product between vectors, but doesn't hold in every vector space, and that's something very special. Okay, so we are at this point just focusing on one operation, and that's addition. Okay. Okay, the third property is that this addition again has an identity element. So for any vector v, there is another vector. There exists a vector such that for any vector, if we add them, we would get the same vector v. And that's the vector 0. So for example, if we go back to our simple example where our vector space is just R2, this vector is just the vector with two components, 0 and 0, right? Okay. The other property is, again, having an inverse element. For any vector v, there should be another vector, which if we add them, we would get this vector 0, and that other vector is just minus v. Again, in the case of R2, if you take a vector like 1 and 2, its inverse is just -1 and -2. Okay. Okay. Now, there is another multiplication, which is not multiplication between two vectors. There is a multiplication between, just as I said, between one element of the field and one vector. Okay. So if A is something in the field and V is a vector in the vector space, we can define A times V. So for example, if as an example, if we take the set of our field to be just a set of real numbers, and if we take our vector space to be R2, it's just the example I told you. A can be something like 2, and this vector V can be something like 1, 2, okay? And the multiplication would be just multiplying each component by this number a. Now, this multiplication should also have some properties. If I multiply this vector v by a number b and then multiply it by a number a, it should be equal to this other multiplication. If I first multiply a and b and then multiply the result by v. And this is a little bit tricky. You should note that although here I'm writing a, b, v, the multiplications which are kind of hidden here are multiplication in different spaces. Here, when I say b times v, here, I am multiplying one element of field by one element in the vector space, right? And again, the result would be a vector. So again, when I'm multiplying that result by a, it would be again multiplication of something which is in the field. A is in the field, and bv is a vector. So here, I never really multiply two elements in the field. Whereas in ab times v here, this multiplication is a multiplication in the field. I'm multiplying two elements in the field, and then I'm multiplying that by something in the vector space. Again, if you just think about R and R2 and R3 and things like that, these properties are fairly trivial. But in kind of more abstract mathematics, or even sometimes in applications, we would work with fields and vector spaces, which they are not very trivial. Okay. The other property is that any field, as we said, has an element which is multiplicative identity. And the property we like to hold is that for any vector v, if we multiply that by this number 1, this vector should not change. Finally, the multiplication of an element in the field by two vectors. If I add two vectors, say u plus v, and I multiply that by a number a, it should distribute. So it should be a times u plus a times v. And the other thing is that if I add two numbers, so these are in the field, and multiply that by a vector, again, it should be equal to a times v plus b times v. Whenever I have all these properties, I would say I have a vector field. I have a vector space over a field. Let's look at a few examples. So as I mentioned, the trivial examples are the spaces Rn over R. This is the most basic example of a vector field. And similarly, Cn over n, over C. This is a complex vector space. Now, there are some kind of more non-trivial examples. Let's look at one example. Let's look at one example to see if we have a vector field or not, a vector space over a field or not. So let's consider R3. We know R3 with its ordinary addition is a vector space over R. Now let's consider a little bit non-trivial example. Rather than the usual addition which we have on R3, which if you take two vectors, A1, B1, and C1, plus another vector, A2, B2, C2, I would usually define this to be A1 plus A2, B1 plus B2, C1 plus C2, right? That's the standard addition on R3. Now here I would choose a non-standard addition. So rather than taking this as definition, I would define another addition. So this is the standard one. and this is really a vector space, I would define another addition. I would define A1, B1, C1. I would define addition to be this new thing. Maybe I put a prime here to show this is not the same as a standard one. I would define this one to be the third root of A1 plus third root of A2, and then I would raise it to power 3. And similarly for other components. Okay, now I have a new definition for addition of elements in R3. Okay. Again, I can multiply any element here, say A1, B1, and C1 by a real number. Say R is a real number. Again, I would define a new multiplication. That's why I'm using prime. So rather than saying this multiplication is RA1, RB1, RC1, where R is an element, say in R, rather than that, I would define it R cubed A1, R cubed B1, R cubed C1. So now we have a new addition and a new multiplication by elements in the field. And the question is that if I take these two new definitions for addition and multiplication on R3, would I end up with a field or not? Is R3 with this new addition and multiplication a field or not? Sorry, a vector space over a field or not? Is this a vector space over the field R or not? That's the question. Now, I want you to think about this for a few minutes. What we should do is we should go back to look at the axioms we have for a vector space over a field. And we should check if this new R3 with these new operations, if they satisfy these axioms or not. Okay, so think about that for a few minutes.
I mean, I think it's no.
Okay, which one is the property that this space as a vector space would fail?
I started with additive associativity, and well, if you try to just check one element of a vector, one element of a given vector A1, just say like A11 or something, you would find that basically what happens is that you would be adding, say, the first element, A11, with the cube root with the cube root of A12 plus cube root of A13 cubed, but if you just reverse the if you just reverse the parentheses, you would find that you would be adding a cube root of A1 plus cube root of A2 cubed plus A3, and I don't believe there's any guarantee that either of those two are equal. So,
okay.
Sorry for the floppy explanation, just trying to make something up as I go along.
Okay, thank you. Okay, let's see that. Okay, so the claim is that this space R3 with this new addition and this new multiplication would fail associativity for addition, for this new addition. Okay, let's see. Let's take three vectors, A1, B1, C1, A2, B2, C2, and A3, B3, C3. What would happen if I add the first two vectors first and then add the third one? Okay, so what I should do is I should first compute this first addition, and all of them are with prime. So what would I get? I would get the third root of A1 plus the third root of A2, and same thing for other components. Okay, that would be the result of this first addition. Now, I should add this other vector. Now that's the thing. So it doesn't matter how do these vectors look like. The formula we had for addition says we should always look at the third root of the first element. So I should look at this first element. This is the new element I'm working in. I should always just write this component here, which is this, and look at its third root, and then add the third root of A3. Right? Is that correct? So if I call whatever I have here X, the addition should be the third root of X plus the third root of A, and then at the end I should raise that to power 3. And then I should raise this to power 3. Do you agree? Is there a question here? Okay. So I should do the same thing for other components. But before doing that, note that this power 3 here cancels the third root here. Is that clear? They just cancel each other. So if you raise something to power 3 and then take the third root, they would cancel each other. So I can just erase that. So that's what I'm going to end up with. Same thing holds for the second component. It would be whatever I have here, the third root of that. So I should write the third root of whatever I have in the yellow rectangle, which is the third root of B1 plus the third root of B2 cubed. And then I should add the third root of the second component of the second vector, which is the third root of B2. And then I should raise it to power 3. But similar to the previous component here, the power 3 and the third root, they cancel each other. So I can just erase them. Same thing holds for the last one. So it would be C1, the third root of C1 plus the third root of C2 plus the third root of C3 raised to the power 3. But on the other hand, here I still have parentheses. First, you see I'm adding, for example, here the third root of A1 to the third root of A2, and then I'm adding third root of A3. Although here I have parentheses, but here it really doesn't matter because these are just ordinary real numbers. It's just ordinary addition, which we do every day, right? So this thing here, if I first add these two numbers and then look at this third one, it would be equal to this other thing that first I would add the third root of A2 to the third root of A3, and then add the third root of A1. They are equal. Same thing holds for second and third components, okay? So in this way, what I can see is that if I take 3 vectors, A1, B1, C1, and then add it to A2, B2, C2, and then add the result to A3, B3, and C3, I would end up with the third root of A1 plus third root of A2 plus third root of A3 cubed. Same thing for the other component. Now, if I want to show this space with this addition is associative, what I should do now is look at A2, B2, C2 plus all these additions, they have prime. I'm just using prime to say this is not the ordinary addition. A3, B3, C3. And then look at A1, B1, C1, and add that to the result. Okay, so right now I wouldn't do anything with the first vector. I would just add the second and third vectors. And this rule we have, it says the result would be the third root of A2 plus the third root of A3, the whole thing cubed, the third root of B2 plus the third root of B3, the whole thing cubed, and then the third root of C2 plus the third root of C3, the whole thing cubed. I'm adding it to this other vector I have, A1, B1, C1. Again, the rule says the third root of A1 plus the third root of whatever is the first component of the other vector, which is this number right here. We should just write that all here. The third root of A2 plus the third root of A3, the whole thing raised to the power 3. Again, note that the power 3 here and the root, the third root there, they would cancel each other, right? So I can erase them. They cancel each other. Same thing holds for other components. Sorry, the whole thing was raised to the power 3. And so exactly the same thing holds for other components. So now the question is that, are these two vectors, this blue vector up here and this other green vector down here, are these two equal or not? And they are equal because, well, this is just addition of numbers, ordinary addition of real numbers. So they are associative. There is no need for parentheses. And as you can see, they are equal. So the green one is equal to the blue one. And that means the addition here we defined, although it doesn't look like the natural addition we have, but it is still associative. Is there any question about this part? Okay. So at least we have one property of being a vector space. The fact is that, well, I mean, you can check everything to see if it's a vector space or not. I'm not going to do that because it's a good exercise for you to think about. Maybe I would do one more property. Let's just check one more thing. So commutativity is simple. I'm not going to do that. Let's try to see. Okay, let's see if, well, one property was that if we take a real number, say R is a real number, okay? And if I take two vectors, say u and v, and if I add them, this multiplication should distribute. And also, if I take two real numbers, say r and s are two numbers, and if u is a vector, s times u and then r times su is supposed to be equal to rs, which is, this is a multiplication as elements in our field, which is r, and then multiplied by u. Check these two properties. Let's see if these two properties of vector spaces, if they hold here or not. Okay, think about that for a minute.
Are we saying that that distributes, that primed one distributes?
Yeah, so this multiplication is this new multiplication I defined. And here again, we have a multiplication. That's actually interesting. Thank you for asking this question, because here I have multiplication between an element of our field, which is R, and an element of the vector space. It's a vector. So this is the new multiplication I defined. If you look at inside parentheses, again, we have multiplication of an element in the field and a vector. So this is, again, the prime multiplication. Similarly here. But here, RS, they are both real numbers. And I didn't change the definition of multiplication of real numbers. So this is just the ordinary multiplication. So on the left-hand side, two of the multiplications are those prime multiplication. On the right-hand side, one of them is just the ordinary usual multiplication. And we want to see if these two properties hold here or they don't.
Okay, thanks.
Yeah, you're welcome. Okay, since we don't have much time, let me just write at least one of them. So let's, for example, let me show r times u plus v. Let's see if it's equal to r times u plus r times v. Okay, so on the left-hand side, I should first look at the addition of u and v. Let's say u is equal to a1, b1, c1, and v is equal to a2, b2, and c2. So the left-hand side is equal to this quantity. Okay, so just by the definition we had, the sum of these two vectors is equal to third root of a1 plus third root of a2 cubed, third root of b1 plus third root of b2 cubed, the third root of c1 plus third root of c2 cubed. Okay. Now I should multiply that by r, but remember the kind of multiplication we defined was this. It's equal to r cubed times the first components. So I should multiply each component by r cubed. Okay. Now look at the first component. I have r cubed times another number cubed. So I just write it here. We know, say, a cubed, b cubed, for any two numbers a and b is equal to a, b cubed, right? So what I'm going to do is, rather than writing r cubed times another thing cubed, I would write r times the third root of a1 plus third root of a2, the whole thing cubed. I would do the same thing for the second and third components. Okay. Now, these multiplications here are times the other number. These are just the ordinary usual multiplication. So, so I can just distribute that. That would be equal to r times the third root of a1 plus r times third root of a2, the whole thing cubed. I wouldn't write the same thing. The same thing holds for the second and third component. Okay, so if I want to, so look at this number here, r times third root of a1. This is equal to r cubed a1, the third root of that, right? Just a simple computation. So this vector is equal to r cubed a1, third root of that, plus r cubed a2, third root of that, the whole thing raised to the power 3. And same thing is correct for the second and third component. Now look at that. This is, we have the third root of one number plus third root of another number, and then we raise that to power 3. This is exactly what we defined when we defined the addition of two vectors. This is what we defined as addition of these two vectors. R3A1, R3A2, R3B1, R3B2, R3C1, R3C2. Because we would look at the third root of first one plus third root of second one, and then we would raise it to the power 3. Right? On the other hand, the first vector is just our definition of multiplication of a vector by a number plus multiplication of the vector, of the vector a2, b2, c2 by the number r, right? The way we define this multiplication is by raising that number and then multiplying by the components. So if we look at the point we started to the point we just reached now, we will see that we proved r times this vector a1, b1, c1 plus this other vector a2, b2, c2 would be equal to r times the first vector plus r times the second vector. So multiplication distributes over addition. I think we don't have any time left. Actually, I'm 2 minutes over time. So is there any question?
Yeah, will you post this on Blackboard, the notes for today?
I do. I would post the video both on Blackboard and also my YouTube channel.
Okay, thank you.
Yeah. Yep, you're welcome. Also, don't forget, you can attend my office hours and MLC hours, which both of them are on Friday. You can find that on my homepage or on my on the page of the course. Okay. If there's not any more questions. Yeah.
Wait, should I? Basically, the answer of it is a field, right?
Say again.
The answer to whether the new vector space is a field, right?
It's a vector space over a field. Yes, it
Okay.
does satisfy the other axioms too, but it would be a good practice for you to check that. Okay, let's finish the class here. You can ask me any questions you have on Friday during my office hours or MLC hours. Okay, have a good time. Bye.